My name is Peter Burno. I've done work with steam all my life. I've carried on a lifetime love affair with machinery, and a lot of it has been steam machinery. When I was a little boy, my grandfather took me around in the city of Chicago and Blue Island to all the construction sites, and I remember the steam drag lines digging the Sag Canal, steam pile drivers driving pilings for buildings in Chicago, and steam cranes excavating for buildings in Chicago. It was truly an age of steam, and after all, steam is the thing that made our country great. It brought us from human and animal power into the machine age. We'd like to talk a little bit today about pile drivers and pile driving. Pile drivers are very old. They go back to the Roman times, about the time of Christ. Roman engineers realized that there were some areas of the earth that were not firm enough on which to build the massive weight of masonry construction that the Romans were famous for. And they needed some way to either transfer that weight down to a firm strata of earth or stiffen up the surrounding earth to the point where it would withstand the weight of the structure. And piles were the way to do that. They were usually wood driven into the ground, and they were driven quite commonly by hand. No great formulas were used. You just drove them in until they wouldn't drive anymore with whatever equipment you were using. Sometimes it was a piece of a log that four men would lift and drop on top of a pile. Excavations were made as the pile went down so that the men could still operate. Later on, a little more sophisticated pile drivers came into being. You would select a couple of saplings and erect them one on either side of the pile that you were going to drive, and then pick up a weight, sliding on those saplings and drop it on the pile. The Romans used pile driving to great advantage in building the aqueducts and the structures that they used. It wasn't until from the 13th to the 15th century, there was a group called the Brothers of the Bridge, and they actually were the first people to lend engineering as we know it today to foundations and the driving of piles. They designed arches, and they would build one span of a bridge every year. In the spring, when the water was high, they would get their materials to the site, quite often by water, blocks of stone, trees that they would later hew out as timbers for supporting structure, and more trees to be used as piles for the foundation. Then in the summer, when the water would be low, they would drive some piles and place trees and brush in between them to dry up the area that they wanted to drive the piles in, to put the foundation on. And in doing so, they would erect whatever type of equipment they deemed proper. It could be a couple of saplings, or later on, more sophisticated systems were used. They actually hewed the saplings to form a set of leads, like 12 by 12s or something in that nature, the length of a tree, and between those and bracketed to them, they would place a log that would be lifted by men. The next step in the evolution was to lay out a rope, which was handmade at a rope walk, a very ancient way of making rope, but very effective. Incidentally, in this country, rope walks were used, and the first steel cables ever made in the world were made by hand on rope walks. Then they would use animal power to pull the rope and lift the hammer, and they would trip it at some point and drop it on the pile. At this point, one of the secrets of pile driving was learned for the first time. And it's a secret that's very easy to understand, but very difficult to make people believe. The crux of this secret was that when you're driving a pile, as long as you're lifting a log and dropping it on a pile by manpower, men can only lift the log about so high. When ropes were added and the pile hammer was lifted by horses, it was possible to lift it to whatever height the leads would permit. And as the pile was driven further and further into the ground, a greater height of lift was possible. And it was found then that the energy was so fast that instead of driving the pile, a great deal of the energy was dissipated in compressing the pile. This was a mystery to engineers for many years, but by empirical rule, they found out that if you only lift a hammer 4 or 5 feet and drop it, it was more effective than lifting it 20 feet and dropping it. Today, we know a little more about this, but I'll come back to that later. In the history of pile driving was first done to form a good foundation, and that's its principal use even to this day. We might ask at this point, what is a pile? Well, a pile may be considered an extension of a foundation downward to a point where firm, bearing soil is found. And how firm does that soil have to be? Well, it depends entirely on what you're going to build on it. If you're going to build a skyscraper, it has to be pretty firm. If you're going to build a highway bridge, it's usual to drive piles to a bearing load of about 15 tons each for a highway bridge. And because of the nature of pile driving, actually by the time you drive a dozen or so piles for a foundation of just a small highway bridge such as we see on the interstate, why, under every pile there's a bulb of compression. And as you drive a series of piles, the bulbs interlock each other, and the bulb of compression on the earth under the pile becomes much larger. So the sum of the piles is greater than the number of each individual pile. The foundation becomes more secure as you go. Pile driving is not an exact science, because even though you may do test borings, you don't know really what's down there in the ground. And it's common to use a factor of safety of from 4 to 6 when you're driving piles. And again, it's pretty much up to the engineer and his experience whether a factor of safety of 6 is enough under certain conditions, or, contrary-wise, on a very large building where you can do a lot of exploration and soil mechanics, if the factor of safety might even be reduced to 2. There's a wide range there, and it takes a great deal of judgment for an engineer to know just what is needed. As far as piling is concerned, the first piles were just logs cut from trees, or quite often saplings, which were a little more easily handled. And to this day, probably the majority of the piles driven in the world are still just that, just wooden poles. A little more sophisticated. Today we can turn them, we can shape them as we want. Oddly enough, you do not usually want to point the pole for a pile. You'd think it would penetrate the ground more easily if it were pointed, but the problem exists that if you put a sharp point on the pile, it's more easily deflected by a rock and usually will not drive straight. If you just have a flat end on a pile, it has a much better chance of driving right straight down. Of course, if you hit a huge boulder somewhere and it glances off the edge of it, nothing will help you. But a pile has a lot better chance of going straight if it's just flat on the bottom. In looking at what piles are, we can say that there are basically two kinds of piles, and we're talking about piles to support a foundation for a building or structure of some kind. One type is a friction pile, and that's a pile that's driven into the ground, and as the driving progresses, the soil is compacted as the pile compresses the soil and drives it to the side, to the point where the friction of the soil against the side of the pile is sufficient to support the weight that the pile is going to be called upon to support. The other type of pile is a pile that's columnar in nature. It's driven into the ground down to some foundation, such as bedrock or stiff clay, something that will support the weight to be placed on it, and it acts more as a column. It's also called an end-bearing pile. Now, the majority of piles are, in reality, a combination of these two. You have some end-bearing capability and some friction capability, and the type of ground through which you're driving depends on which predominates. But there's usually a combination of the two that make up the capability of the pile to support its load. Piles today take many forms. The majority of piles, of course, are still wood. Sometimes wood is covered with heavy screen mesh and gunnited with concrete to protect the pile, particularly along the seacoast where marine borers will ruin a pile, will eat through a pile, sometimes in a matter of less than a year. Other piles might be tubular pipe, which is very common today. It has the advantage of being able to be driven, be welded in sections, be extended as necessary. Oftentimes when you start driving a pile, you need a certain bearing load. You know that the load that the building is going to place on the pile, you know how much that pile has to withstand, so you know how hard it must be driven. And if you figure you're going to drive a pile 40 feet and one pile hits a good bearing at 35 feet, you can cut the surplus of pipe off. And a few piles down the line, you might have one that has to go 70 feet. Well, you can just add some more to it by welding. So pipe is a very common pile. Some piles are made of H-beam, and that's used today quite often in large structures. Your biggest piles today are made of pre-stressed, precast concrete, and some of those can get very large. They have quite a bearing loading, and they can be extended to whatever depth is found necessary. These piles are commonly used on big buildings, bridges, railroad trestles, that sort of a thing, and as such, why, the pile itself, being very heavy, requires a very heavy hammer to drive it. Now we can get back to our discussion on a high fall of a drop hammer and a low fall of a drop hammer. When you're driving a pile, a certain amount of energy is necessary to make the pile move. But even more than that, you need to have the right kind of energy. Let's try to drive a pile, and we have determined that it will take 1,000 foot-pounds of energy to drive this pile. Now we have 2 hammers available, and of course this is never done in practice, but just in theory. and this will demonstrate what I'm trying to say. Let's say that we have a 1,000-pound hammer with a 1-foot stroke, or a 1-pound hammer with a 1,000-foot stroke. Each one of these hammers is capable of generating 1,000 foot-pounds of energy. But the velocity of a 1-pound hammer falling 1,000 feet, neglecting air friction and such things as that, will be so great that the hammer blow will simply compress the upper part of the pile. And unless that blow delivers its energy all the way down through the length of the pile to the very bottom, the pile will not move. So therefore, what we find is that the old way of 4 or more men picking up a log and dropping it on a pile really wasn't so bad in theory. A low velocity blow is what's really needed. Now, if you have a low velocity blow, you're limited as to how far a hammer can fall. So the answer to getting the energy necessary to drive the pile manifests itself in finding a heavier hammer. And with the coming of steam engines and steam donkey engines and hoisting engines, this became entirely practical. Many pile drivers were built with some as simple as just wooden leads, and some with very sophisticated steel leads, and some as high as 130 feet, to carry a drop hammer that could only fall 4 or 5 feet, but in doing so was so heavy that it was capable of driving the pile, whatever the pile happened to be. In my own experience, one big job was done with steam hammers, and we used my rig number 7 to drive these piles. It was mounted on a barge. The piles were precast, pre-stressed concrete, octagon in shape, 42 inches across the flats, and 90 feet long. As massive as these piles were, in some places we had to drive them 3 piles deep. To do this, and to make sure that the energy was sufficient to drive the pile of that great weight, and at the same time the velocity was low enough so that the top of the pile wasn't all beaten to pieces or the concrete spalled or deformed, it was necessary to use a very heavy hammer. And at that time we used what was then the largest hammer in the world. It was a steam hammer, single acting. That meant that the steam lifted the hammer but let it fall of its own weight. So the steam did not add any velocity to the fall of the hammer. Called a single acting hammer. The hammer weighed 66,000 pounds, and the hammer ram, the weight of the striking parts themselves, weighed just over 30,000 pounds. It was a very massive hammer, and it performed beautifully. In using a single-acting steam hammer, and this is the hammer that we're using on the rig today in the picture, it's interesting to note that half of the weight of the hammer is in the striking parts, and the other half is in the stationary parts. The striking parts would be the piston rod, and the ram itself, whereas the stationary parts would be what holds the whole thing together, the steam cylinder, the guides, and the base. If you look at the geometry of how they work, or the physics of how they work, then probably it becomes easier to understand if we think of the armor-piercing bullet developed for naval use during the war. Conventional bullets just were shot at a ship, and the ship was heavy enough that the bullets really didn't do any damage. They caused a dent in the ship, and that was about it. The armor-piercing bullet used an altogether different principle. At first, they tried to make armor-piercing bullets very hard, and the harder they made them, the less damage they did. And then somebody came up with the idea, well, an armor-piercing bullet has to be two things. It has to have a very hard interior and a very soft exterior. And the philosophy of that was that when this shell hit the side of a ship, it was soft and put a great stress on the ship's plates. And then while that stress existed, the hard part of the bullet passed through the soft part and punctured the ship. And it worked. Now we're doing this same sort of thing in a single acting hammer. And for the heaviest pile driving that can be done, a single acting hammer to this day is the kind that's always used. The dead weight of the hammer preloads the pile, so there is a load on the pile beyond its own weight. And while that load is on the pile, the striking part of the hammer, which is about half the weight of the hammer itself, strikes the pile. Now, if you were to try to increase the velocity with steam driving the hammer down, what would it do? Well, to every action there's an equal and opposite reaction, so what would happen is the force of the steam driving the hammer down, overcoming the inertia of the hammer, would actually lift the stationary part of the hammer from the pile. If it didn't lift it clear off the pile, it would diminish the weight that was on the pile, and the loading of the pile would not be as great. So, in heavy work, a single acting hammer is the hammer that you really need. Among other types of piles today, we have sheet piles, steel sheeting. It's just a steel form, fairly thin, and when I say fairly thin, anywhere from 3/8 of an inch to 3/4 of an inch, but it's ribbed for strength. And that type of piling is usually not used as a bearing pile. It's driven into a formation and driven down to the point where the sand or clay or whatever it is that makes up the formation is so tight that water cannot penetrate it. And the very act of driving the pile tends to tighten it to a certain extent. And this is to stabilize earth that might have a tendency to flow. This sort of thing was done for the Twin Towers in New York. When they were built, the land under the Twin Towers was very unstable. It was part of an old riverbed and still had mud flowing under it. They drove sheet piling in sections around the building, excavated these cells between the sheet piles, and then introduced a grid of mesh, wire, and reinforcing rod, and then pumped them full of concrete. And doing this a step at a time is what caused the river flow to be shut off, and the building could then be excavated inside of this concrete cofferdam that now surrounded the foundation of the structure. It was very effective and it worked very well. Well, this is the sort of an application that you would use sheet piling for. When you think of driving a pile, the same philosophy for driving sheeting exists for driving a heavy pile. If you're going to drive to a great depth, you need a single acting hammer. If you're going to just drive to make room to work in a sewer or something like that, no great depth is involved, then a double acting hammer will work. But in all cases, we go right back to the oldest technology in pile driving. It can also be driven with just a drop hammer. You can pick it up with a cable and drop it on the pile. And if you don't pick it too high, it'll drive the pile successfully. With all the technologies, you can go right back to the old drop hammer. Everything still works the way it worked with the drop hammer. You pick the hammer up, drop it on the pile, and drive the pile. And as long as you don't pick it over 4 or 5 feet, it'll work just fine. Large falls result in either large sets of a pile or broken piles. And short falls result in a good, steady driving and a good bearing load when you drive. On our rig number 7, right now we've scaled that down more for demonstration purposes than anything else. It's the only place I know of where people can actually go and see a big pile driver at work, actually driving piles with a steam hammer. We've scaled it down so that we can just drive ordinary wooden piles. Before, that machine had leads 130 feet high and handled a 66,000-pound hammer. Well, when you're playing, you can't drive big piles like that cost thousands of dollars a piece. So this way, the machine still puts on a good demonstration, and it teaches people what pile driving is really like. It's steam operated, of course. The boiler can carry up to 225 pounds of steam pressure. It's capable of operating not only the hammer, but when we had it on a barge, it took care of all the steam auxiliaries on the barge. The 4 deck engines, one at each end of the barge and one on each side, and also the air pumps for divers and a decompression chamber. That boiler took care of the whole thing, and there was no great problem. You had to keep steam up pretty hard. You had to work a bit, but it did the job all right. When they first started to drive piles with ropes, horses were used, and in my lifetime, one time I had occasion to use horses for driving piles. You had to lengthen out the tugs, and you built a trip mechanism into the double trees, and you'd use a team of horses to hook onto a loop in the rope or cable, pull it out about so far, and then you'd trip it with a trip rope, and you wanted those tugs far enough back so that when the double trees fell to the ground, they didn't hit the back legs of the horse. Now, pulling a wagon, that would not be a problem, but driving piles, it could be quite a problem, and it would scare the horses. It was a wonderful experience. You tend to learn a lot about just how piles were driven, just like learning combustion. There's no better way than firing a hand-fired locomotive. You learn just what to do. Using this rig, we've done just about the gamut from driving sheet piles to driving these monstrous concrete piles to driving wooden piles. The rig was built in 1905. It was built by the American Hoist Derek Co. It has a 3-drum steam donkey engine. The drums are capable of 15,000 pounds of pull per cable at the drum. It's capable of handling anything that a pile driver would have to handle. We use one drum to pick up the hammer. We use the second drum to pick up the pile, and obviously you have to pick the hammer up before you pick the pile up, otherwise you have no place to put the pile. And it has a third drum for whatever purpose we might need, and sometimes when we're picking up big piles, where the length of the pile is so great that the pile would break of its own weight when picked up horizontally, we have to use the third drum as well as the second drum, and rig pulleys between them so that we actually pick up the pile in as many as 6 different places. And we have done that with that machine. When we brought it here, we built a new set of leads for a number 1 hammer. They're 20 inches across, which sort of limits the size of the pile to that dimension. The machine has worked on these grounds now for almost 35 years, and it's still maintained, still inspected annually, is ready to go to work anytime we have a job that needs it. We just haven't found a big job in the last 30 years, and we might never again. This is a good place for it, and probably for the next millennium. People can come here and watch a machine work that was built before they were born, but yet this was the kind of a machine that made America the country that it is. This is the innards of the pile driver right here. This is the mechanism that does all the work. Basically what this is a steam donkey engine. They were used for many purposes. The logging industry used a lot of them, the construction industry used a lot of them, and donkey engines are used to this day, although they're usually no longer steam. But for driving piles, steam was a natural. Here we use steam for everything. We have 3 drums. The first drum over there handles the pile hammer. The second drum picks up the pile itself, and the third drum is just an auxiliary for whatever we want to use it for. Sometimes we may use that drum to move the machine ahead or back, depending upon where the next pile is. We might use it if we're on heavy pile driving work, handling heavy piles that can't be picked up with just one line. We may use it to help the second drum pick up a pile. Or whatever you need it for, it's there. It's handy to have. Here we have the cylinder of the engine. There's another one just like it on the other side. This is the lubricator that pumps oil into the steam to lubricate the valves and the piston, and also the throttle valve right here. A crosshead, a connecting rod, and a crank disc. This is a single eccentric engine. The eccentric rod, that drives the valve rod here. The engine will only turn in one direction. Well, since you can't push a cable, one direction on a machine like this is all we need. Now these are the clutches for the various drums here. And these are the brake pedals for the drums down here. And then these are ratchet levers. When we set one of these levers up, why, that puts a ratchet on the drum so we can hoist, but the drum will be held in that position. It can't lower. And then we'd have to catch the drum on the clutch and on the brake to release that. This is the throttle right here. This starts and stops the engine, and since it's a double cylinder engine, double acting, with cranks at 90 degrees, there are no dead centers, this engine can exert 100% torque at 0 RPMs in any position. This steam pipe right here has a release valve on it where we can exhaust steam right up through the roof, a drain valve where we can get rid of water, and a throttle valve. And we use that to pipe steam out halfway up the leads through a hose to the hammer itself. That's the throttle valve that starts and stops and regulates the hammer itself. Here we have a backup valve just in case we have a problem and have to shut the steam off. And here we have a valve that goes right up to our whistle. So we can blow the whistle, use whistle signals. If we're on the water, those signals have a carefully set up purpose. If we have a problem, we have a series of short blows. If we're going to start, we use one whistle signal and then another one. If we're going to stop, we use one whistle signal alone. And if we're going to pick up a pile, we might use 3 blasts on the whistle. The main throttle valve is up there where the steam comes out of the boiler and goes down into the engines. The exhaust from the engines goes back up into the boiler and up the stack so that it creates the draft. That's why we don't have to have a 50-foot smokestack on this machine. Just like a locomotive, as this engine runs, the machine chugs, and that chugging is the exhaust from the cylinders going up the smokestack. And then we have a lubricator here so we can give the whole thing a shot of oil by hand when we're starting out. The pile hammer itself has its own lubricating system. and we fill that with steam cylinder oil about once a day. That takes care of it. Maintenance on this machine is quite light. It's due for maintenance again right now. Basically what we'll do is just clean it up, clean off the old cylinder oil that's run down on it and the grease, steam clean it, and then go over the clutches and the brakes, make sure they're properly adjusted. And this time we're going to have to re-babbitt the crankshaft. The crankshaft is starting to get a little bit warm. It's taken down for the winter, but right up here we usually have a steam gauge, and a water column is on the other side, 3 gauge cocks here, 3 more of them over there for the firemen. We're now on the other side of the steam donkey engine in the house of the pile driver. You see the other cylinder here on this side, the connecting rod, and the crank disc. These are the brakes, and there's one for each of the drums, and then these are the winch heads. They turn whenever the engine is turning. They'll turn slowly, and we run a rope right out this door, a rope about 2.5 inches in diameter, and wrap it around this head about 5 times and around this head about 3 times, and then one man can pull it easily. Just tighten it up on this drum will tighten it on that drum, and the rope will move. And we use that rope to swing the house. This house will swing fully 360 degrees. And we just swing it with a rope and a big set of pulleys. It's the way it's been done since 1905, and we haven't found anything better. It works just fine. A steam donkey engine like this, they were built in a number of sizes. This one is an 8¼ inch bore and a 10-inch stroke. Not a very large engine, but the way the drums are geared, it has 15,000 pounds pull on a rope at the drum. Well, 15,000 pounds pull is about all the pull you want on a 3/4 inch rope. We never really use that much pull. 3/4 inch ropes good for 5.5 tons with a factor of safety of 5, and that's about the way we look at it. But the machine is capable of 15,000 pounds on any 2 drums at one time. So it has quite a bit more pull than we really need. Bigger engines were built for high-speed logging, big work in river dredging, that sort of thing. But for driving the biggest piles, this machine is perfectly satisfactory. Gives us all the power we really need. Now we'll go back and look at the boiler, and after all, the boiler is the heart of the whole machine. The boiler is right at the rear of the engine. It's a separate boiler. It's not connected to the engine in any way except by steam pipes. And that means that it's not a donkey engine that you could use in the woods where you just have the donkey pull itself around, and its boiler is mounted right on the engine frame. This boiler is completely separate, and the boiler is much oversized for the engine, and the reason is because it has to handle not only the donkey engine itself, but the hammer and any other auxiliaries you might need. When we had this on the barge, why, we had 4 deck engines, one in each corner of the barge, that handled sea anchors and whatnot to move us around. It also had an air compressor for divers, and it had a decompression chamber. If we had to bring a diver up and put him in a decompression chamber, we had everything right there to do it. And this boiler not only handled the pile driver, the donkey engine, the hammer, but handled all the other auxiliaries on the barge at the same time. And sometimes you had to work a little hard to fire it, but it was plenty big for the job. It did just fine. This is the boiler. It's an ASME boiler, and we replaced this boiler, about 40 years ago. This pile driver is located on the grounds of the Rock River Steam Thrasheree. It's an organization started in 1955 to preserve mainly agricultural, but actually all kinds of steam machinery. On this grounds, We not only have this pile driver, we have what is probably one of the oldest cranes in the world still working. It was built in 1887, and it runs every year at the show. It's also inspected annually and maintained. In addition to that, we have what is probably the world's largest remaining steam shovel. It's in the process of being restored right now. Also, there are steam traction engines, thrashing machines, steam plowing, gas tractors of all kinds and descriptions, almost anything involved in agriculture, a sawmill that's run with steam engines, shingle mills, and there's a building which houses stationary steam engines which are running during the show. Some of these engines, many of which are one-of-a-kind engines, are all there. You can see them run, you can observe them as they used to work, only at a low speed. In this building are also several diesel engines, varying from the 1920s on up through later day diesels. The Thrasheree has its show all 4 days during the Labor Day weekend. And if you'd really like to see some old machinery in action, doing the work that it was designed to do, and operating for the benefit of people like yourself who are interested in seeing this machinery work and learning about our nation's history and heritage, this is the place to come. The Rock River Thrasheree is located on US 51 between Edgerton, Wisconsin and Janesville, Wisconsin. And if you want to get there, the easiest way, if you're coming up Interstate 90, either go to the last Janesville exit and over to US 51, or if you're coming from the north, go to the Edgerton exit, which is Highway 59. Take 59 into Edgerton at the stoplight, turn left, and you're right on US 51, and it's about 5 miles to the Thrasheree. Labor Day weekend, the grounds are well marked, but you can usually see a good plume of smoke above them. That'd be a good guide for getting there. In putting this together, I'd like to thank my friends at the Rock River Thrasheree. I'd like to thank Mr. Chellis, who wrote a very good book on pile foundations, which I have studied off and on for years. And I'd like to thank my very good friend and compatriot Dan Lee, who's responsible for all the taping and getting this all put together and edited and in proper form.